So hello student. So today I am with the new experiment, and that experiment is of the MOSFET. So we are going to plot the transfer and drain characteristic of N channel MOSFET. Okay. So as you know, the MOSFET is a three-terminal device, and the full form of it is a metal oxide semiconductor field effect transistor. So the three terminals are namely source, gate, and drain. Okay. So it is also known as IGFET. This IGFET is insulated gate field effect transistor. So basically here the theory part is written that heavily doped 2n type wells are doped in p type substrate to form source and drain, and between these two type wells a lightly doped n type terminals form a channel. Okay, the thin layer of SiO2, which is an insulating matter, is fabricated on the surface of the channel. Okay, so basically what we are going to do, we are going to make a circuit here. Okay, so this is N channel MOSFET 2N7000. Okay, we are going to provide the positive voltage source VDS. Okay, so VDS will be provided at the drain with respect to the source. Okay, similarly we will provide VGS also, okay, at the gate with respect to the source, and then we will check that what type of characteristic it shows. Okay, so afterwards these are the procedure that for finding out the drain characteristic, what we have to do, we will firstly set VGS at 0, and we will vary VDS at the step of 0.5 volt and note down the corresponding reading of ID. Okay, that is the current here. Okay, here. Now after that thing, we will repeat the same procedure. We will increase the VGS to 1 volt, and we will keep VGS to 1 volt constant. Okay, we will not change VGS. In the first step also, we have set the VGS at 0 volt, and we have varied only VDS. Okay, in the second step we will set the VGS to 1 volt, and then we will vary VDS again. Okay, and similarly for the 3 volt also, or for 4 volt or 5 volt, we will find out the different values of VDS corresponding to ID. Okay, and here is the drain characteristic. We have to write down the value of VDS, okay, with ID, and we have to write here that what we have set VGS every time. Okay, and in the transfer characteristic, what we have to do, we do need to set the VDS, okay, and we will vary VGS at this time. Remember, here in the drain characteristic we have varied VDS, but in the transfer characteristic we will vary VGS. Okay, and we will not change the value of VDS, and we will just change the value of VGS with 0.5 volt increment, and we will find out the value of IDS ID every time, and then we'll plot VGS versus ID for the constant value of VDS. Okay, so this one is the transfer characteristic of VDS. Okay, so we'll move on to the circuit part. So this is my multisim. So I'm just going to find out this MOSFET. It is 2N7000. So here I have just put it here. Now I will connect two voltage source here, one at this side right and one at right left side. Okay, so for that thing, just go to the source, take a DC power at this side, and the another power to be this side. Okay, so from this side we will give VGS. Just change here the name. This one is VGS and this one is VDS. Okay, so VDS would be provided to the drain and source side. Similarly, we will provide the VGS here. Just lower it little bit down. Just provide it here. Okay, so this will provide it to gate and source side. Okay, now we will also provide a ground also here. Okay, so this experiment could be done in two ways. Okay, one way is that for firstly we'll look for this drain characteristic. Okay, so for drain characteristic we can do firstly that we have to keep, remember that we have to keep VGS here constant. Okay, so for first time we could take the value here to be 0 volt, Okay, and we will connect a multimeter here or an ammeter to find out that what is ID. Okay, and for every change of value of VDS, we will find different value of ID here. Okay, and we will write the value of ID and VDS here. Okay, so this could be done. For that purpose, I will just delete it here and I will just use a multimeter here. Okay, since this one is the positive one, so this should be at this side. So just flip it here, flip it horizontally. Okay, so suppose this VDS is currently at 0 volt. So if both of these are 0 volt, the output should be 0 theoretically. So we'll just take it at 1 volt. So when this is at 1 volt, run it, just check. We have got 8.099 millivolts. Sorry, this should be current here. So we are getting a very less amount of current. The current is in picoampere. Okay, so this is very less. So we'll just change this value. Suppose take it to be 4 volt. Okay, and then run it again. So here we are getting again the value here 44.409. Just similarly change the value of VDS every time. Okay, by keeping this VGS 0 volt, right here 0 volt. Okay, 0 volt, and write the value of this ID and VDS every time. Okay, and in for the second column, just change the value of this VGS. Suppose change it to be 1 volt. Okay, keep it to be constant, and again just change the value of this thing. Start from 1 volt. Okay, start from 1 volt to 2, 3, 4, 5, 6, or you could go through a step size of 0.5 volt, like 1 volt, 0.5, 1.5 volt, 2 volt, 3 volt, something like this. Okay, and every time you have to check that what is the value of this thing. Since both are 1 volt, that's why I'm getting this type of current here. Take it, suppose 2 volt. So here we are getting some amount of current. Okay, so we will change the value of this thing every time. Okay, and we will get the value of the current here. Okay, and every time we have to write the value here. Okay, so this is first type, that how to perform this drain characteristic. The second way is that in this drain characteristic only, uh, we could just change this source. Okay, and we will replace it by, in signal we will find a DC interactive voltage. Okay, so here we are getting a key. Okay, so by the help of key we can change the value of this thing every time. Okay, suppose we will run the simulation. Currently we are getting 0 ampere and the key is A. Okay, and the maximum voltage which this interactive voltage can go at, right at this time is 10 volt. We can change this voltage. Okay, the increment is 5%. We can also change the value. Okay, so it's up to us. So just press the keyboard A. Okay, A button of the your keyboard, and when you will press the A button of your keyboard, the value of this VDS will increase. And every time just press the A button of your keyboard. Okay, and you will get the value of ID here. Okay, and every time when you will get the value of ID, just note it down in this observation table, and just afterwards plot it. Okay, so every time I'm going to press the key A, the value is changing. Okay, and then we are getting different values of current here. This is the second way. Okay, and okay, and in this thing now you can just also change the key also here. Suppose I'm going to choose C here. Okay, and suppose I am going to increase the increment by 10%. Okay, so at this time when I will run the simulation, suppose just make this voltage to be 0 volt and run this simulation. So at this time the key is C, so we have to press C button of my keyboard. So after changing this sorry after pressing this key button C, okay, which I have chosen. Whenever I will press C, this increment would be 1 volt, as we already know that 10% of 10 volt is 1 volt, and the maximum value was 10 volt set, and I have increased the increment to 10%. So every time when I will press the key C, it will increase the value of voltage by 1 volt. Okay, so at this for because of this thing also you could change the value and you would get the different value of ID here. Okay, so by using this thing also you could just proceed on, or there is another way. Okay, suppose just firstly stop the simulation, replace this to the same DC source. Okay, that is VDS. We don't need this multimeter now. There is another way also to do this thing, and that is DC sweep. Okay, so for DC sweep, what we have to do, just click on this interactive button. You will find the DC sweep here. Okay, so DC sweep is there. So we are seeing that one source is given, source 1. We will use second source also, as we know that for drain we need both VGS and VDS. Okay, so we'll change both the VDS and VGS. Firstly, we'll choose the VDS. Okay, suppose the start value of the voltage is 0 volt and the stop value, suppose it is 5 volt. Let the increment to be 0.5 volt. Okay, and the second source would be VGS. Okay, its start value is 0, and since we are taking the VGS for 1 volt, 2 volt, 3 volt, so we will choose it the stop value to be 3 volt. Okay, so VDS will also change and VGS will also be changed by the help of DC sweep only. Okay, in the output case, what we have to do, we have to use the ID. Since we need the ID, so ID is basically this IVDS here only. Okay, so just add this ID VDS here. Okay, and run this simulation. So when I've run it, okay, so it is background. Now it is white background. So you can see here we are having three outputs here. Okay, so we can increase the value of these number of lines. Okay, by changing the value of the stop value of this VGS, as VGS will also be run for a higher value of voltage. Okay, suppose I have done this thing. Okay, now when you will run this thing again, just see we are getting many lines. Okay, many output lines for VGS is equal to 0 volt, VGS is equal to zero point 0.5, VGS is equal to 1 volt, 1.5 volt, 2 volt, 2.5 volt, etc, 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 up to 5 volt. Okay, every time this color of the line, the output graph has changed. Okay, and here the color shows that which color the output is present here. Okay, so this is basically flipped up vertically, so we need to flip it up upside down. Okay, so for that thing what we will do, in this DC sweep only, in the output we should be having a minus sign. Okay, so for that thing what I will do, I will just add a expression here. I will include minus sign by double clicking on it. I will double click on IVDS, click on OK. Here minus IVDS is there. Run this simulation. Just see here we have got the drain characteristic of this thing. Okay, so if you want to view the values here, you could use the grid and cursor also. By the help of cursor you can see the values data are present here. So you could use here the cursor and you will see at every point that for what value of this VDS, what is my I or ID. Okay, so you could use the help of cursor also, or you could simply export this thing in Excel. Okay, so in the Excel we do need, suppose we are going to take till VGS is equal to 3. Okay, till VGS is equal to 3, what is the value of ID I have chosen. Okay, you can choose other values also. So I have chosen the value of ID up to the part where VGS is 3. Okay, click on this OK button. It will export all the data to the Excel. Just open the Excel, just see here. So every part here VGS is equal to 0. This X trace is our data, and here y trace is also we are having the data. Okay, so basically uh, this x1, this data, okay, is the value of voltage, and here the y trace is the value of current. Okay, so this one is the data when VVGS is 0. Okay, So here you could write the value of this thing. Okay, so this one is voltage. Okay, so this one is voltage and this one is the current or the ID. Okay, so sorry, this thing. Okay, so what the voltage? Okay, voltage should be here A. Okay, so this one is voltage and this one is ID, that is current. Okay, so we are going to write those data here. Okay, so okay, I haven't written there that this is VDS. Okay, so this voltage is VDS only. Okay, VDS, and this current is ID. Okay, so this is when VGS is 0. Okay, similarly here the data, these two data are present. This one is VDS and this one is ID. Okay, and these data are when VGS is 0.5. Here these data are when VGS is equal to 1. These data are when VGS is equal to 1.5. Okay. So by help of this thing also you could plot the graph here in the Excel also, or you could just export this graph. Okay. So this one was for the transfer characteristic of our MOSFET. Understood? So now if we want to see the, sorry, this one not the transfer characteristic, this one is the drain characteristic. Okay, so now if we want to see the transfer characteristic, we will do that thing also. So for doing that thing, what we do need to do in the transfer characteristic, you could look here, we are not going to change the value of VDS. Okay, we will keep the VDS whatever it is. Okay, and we'll just change the value of VGS, and every time we will find the value of ID there. Okay, so here again in the DC sweep, we are not going to use the second source. We will use only one source, and the one source would be only VGS. Okay, we are not going to change the value of VDS. So at this time, in the output, just remove this thing, as we will get an output here of IVDS. So this is only the ID. Okay, so run this thing. So see here. Okay, this graph is again flip down vertically. Okay, so we will again change the value by employing a minus sign here in the output. Just remove it here, add an expression minus of IVDS. So this IVDS is only the ID only. Okay, so now you can run it, and now you can see here this is the transfer characteristic. Okay, so you can directly take the value of data from here, or you could just export it to Excel part, or you could just export this graph only, as this graph is showing all the data, okay, of VDS and the current ID. Okay, so at this time we haven't considered here the VGS part, and we have kept VGS constant only. Okay, so this is how we have to perform the experiment. We could use all the three way. We could either change the value of the VDS every time. Okay, or we could use replace this thing by the source that is called DC interactive voltage, and we could use the key button to change the value of voltage, and we could take the value of ammeter data every time here, and we could plot it in Excel, or we could use the DC sweep way. Okay, so in either way we can do this experiment. Okay, so I hope you have understood that how to plot the drain characteristic and the transfer characteristic of this N channel MOSFET. So thank you for watching the experiment.